This is my Precalculus course. Today we're going to learn the complex plane and how to graph polar equations using radian units. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. We learned radian units for the measures of angles in my trigonometry course, but we haven't had a chance to review those units yet. Here we have the special angles and the quadrantal angles in degree units, and here we have those same angles in radian units. So these are special angles, and it may seem difficult to remember all these values here, but it's actually not that hard. If you can remember that pi is 180 degrees, well then obviously pi divided by 6 would be 30 degrees, because 180 divided by 6 is 30 degrees. 180 divided by 4 is 45 degrees. And 180 divided by 3 is 60 degrees. So again, pi represents 180. 180, 180, 180. Divide by 6, you get 30 degrees. Divide by 4, you get 45 degrees. Divide by 3, you get 60 degrees. Now, if pi over 6 is 30 degrees, and you multiply that by 5, shouldn't you get 150 degrees? If pi over 6 is 30 degrees, then obviously 5 pi over 6 is 150 degrees, because 30 times 5 is 150. And if pi over 4 is 45 degrees, then 3 pi over 4 should just be 3 times 45 degrees. So that would be 135. And if pi over 2 is 90 degrees, then if you multiply pi over 2 by 3 to get 3 pi over 2, then that should be 270 degrees, because 90 times 3 is 270. So remembering these values is really not as difficult as you might think. So I want you to get a picture of all this information here. We're going to use this throughout the class. So now we're going to use radian units with polar coordinates. So it says, draw the points described by the polar coordinates below, then convert the coordinates so that each angle measure is written with radian units rather than degree units. So first we're going to graph the point. So we have 2 here, so we're going to count 2 out on the x-axis. Remember, this number is always the horizontal movement to the right or to the left. If it's a negative number, we move to the left on the x-axis. If it's a positive number, we move to the right. So we're going to move 2 units to the right, then we're going to rotate 135 degrees, and that's going to put us somewhere over here. So the point that we're looking for is roughly about there. So that is the point 2, 135 degrees. So now we're going to convert the angle to radian units. So let's look up here. 135 degrees is equivalent to 3 pi over 4. So we're just going to change that to 3 pi over 4. So here's the point using radian units. This number doesn't really change. It's still whatever value we started with. So let's try another one of these. We're going to count to the left 1 unit, and then we're going to rotate counterclockwise 180 degrees, and that's going to put us right there. So that point would be roughly about there. I'm exaggerating the size of the dot there. just so we can see better. So 180 degrees is pi. So the point is -1 pi. So let's try a couple more of these. So we're going to count 3 units to the left, or excuse me, 3 units to the right. Then we're going to rotate -210 degrees. So that's rotating clockwise when we have a negative number. That's going to get us to about there, roughly. So that is the point plotted there. And we're going to convert -210 to radian units. So 210 is 7 pi over 6, if you can see that there. 7 pi over 6. So it's just going to be -7 pi over 6. Now, let's try number 4. So we're going to go to the left 1/2, and then we're going to rotate in the clockwise direction, and that's going to put us right about there. So our point is about there, roughly. And probably should move that down a little bit. So using radian units, we have -1/2, comma, -pi over 2. And how do I know that? Well, because 90 degrees is pi over 2. You need to start to get used to these different units here. Okay, so let's try a couple more of these. Okay, so I want you to try number 5. You can use the information at the left and numbers 1 through 4 to help you. Go ahead and attempt number 5. When you come back, we'll do it together. Alright, we're back. So we're going to move out 3 units to the right and then rotate 240 degrees counterclockwise. And that's going to get us about here, roughly. So again, these, well, the position doesn't have to be exact. You don't have to get a protractor out. And so 340 degrees in radian units would be 4 pi over 3. So 4 pi over 3. If you got that right, excellent. Go ahead and try number 6. When you come back, we'll do it together. Alright, we're back. So we're going to move 1 unit to the left and then rotate 270 degrees counterclockwise. So our point, as you can see, is right there. And now let's write the angle in radian units. So let's look at 270 degrees. In radian units, that's going to be 3 pi over 2. Okay. So try number 7. If you got number 6 right, good job. Try number 7. When you come back, we'll do it together. Okay, we're back. So I'm going to move out 2 units to the left and then rotate counterclockwise 45 degrees, and that gets us to about there. So we have our point graphed, and now let's change 45 degrees to radian units. So 45 degrees would be there, so that's pi over 4. So if you got that right, excellent. Go ahead and try number 8. When you come back, we'll do it together. Alright, we're back. I'm going to move out 1 unit to the right, and then I'm going to rotate counterclockwise 180 degrees, and that gets us to here. So if you got that right, excellent. So we have negative pi. Remember, 180 degrees is pi. Okay, so those were all special angles, or quadrantal angles. Quadrantal angles are special angles, by the way. But here we have an example where the angle measure is not special. It's not a quadrantal angle. It's not a multiple of 30 or 60 or 45. And so how do we do this? Well, we're going to have to use our conversion factor. Remember, we learned the conversion factor. If we're trying to convert to radians, we multiply by pi over 180. And you're going to do this in chemistry courses primarily and physics courses. This is called the factor label method. You label pi with radian units, and you label your degrees with the degree symbol. So you're multiplying by this factor, and you have your label. But when we write radian units, we typically don't write the unit. Radians are considered to be numbers that really don't have units, even though we call them radian units, but you don't have to write the unit. Scientists and engineers and mathematicians have decided that. So let's multiply. We get 200 pi over 180, and the degree units just cancel out. That's how the factor label method works. It helps us to remember what operations to perform. So we can now divide both sides by 10 to reduce the fraction, and now we can divide both sides by 2, and there you go. That's not the answer though. Let's write the answer up here. So we have 2 comma 10 pi over 9. Okay, so we forgot to actually graph the point. So let's count out 2, and then we're going to rotate 200 degrees, which would get us somewhere around here. So again, the position of the points that I'm drawing here may not be exact, but it doesn't need to be exact. This is just explaining the basic idea of how to use radian units with polar coordinates. Okay, so we plotted the point and we converted the coordinates to radian units. So let's try one more of these. So we're going to move 3 units to the left, and then we're going to rotate counterclockwise negative 210 degrees. So this is 180, and then a little bit more, and it's going to be something like that. So our point's going to be somewhere around there, and we need to do the math to convert negative 211 degrees to radian units. So we're going to multiply by pi over 180 degrees. Now if we wanted to change radians to degrees, we would flip this. So if you have like 20 degrees, for example, and you want to change to, if you have, let's say you have pi over 6 radians and you want to convert to degrees, you would flip this around. And the pi's would cancel out, and you would get 180 over 6, long story short, 30 degrees. So, but we don't need to do that in today's class. So we end up with 211 pi over 180, and we can just leave it in that form. And actually it should be negative. I forgot to write my negative. So we can change the angle measure in the ordered pair to negative 211 pi over 180. So there we go. And we can't reduce this fraction. So I want you to try number 11. When you come back, we'll do it together. Okay, we're back, so I'm going to count 3 units to the left. I'm going to rotate negative 20 degrees, which would bring us to about there, roughly. So we graph the point, and now we need to change negative 20 degrees to radian units, and we get negative 20 pi over 180. If we divide both sides by 20, we get negative pi over 9. So that's the angle measure in radian units. So if you got that right, excellent, very good. Try number 12. When you come back, we'll do it together. Okay, we're back. So we're going to move 2 units to the right and rotate 35 degrees. That will get us to about there, roughly. And we need to convert 35 degrees to radian units, but we can't do that without this conversion factor because we don't have a special angle here. 35 degrees is not a special angle. So we have 35 pi over 180, and if we divide both sides of that fraction by 5, we get 7 pi over 36. So our point is going to be 2 comma 7 pi over 36. Alright, so if you got that right, good job. So now we're going to do some review with our basic trig functions using radian units. So you should be pretty familiar with these functions, and we're only going to do problems here with special angles or quadrantal angles. So we have sine pi over 3. We need to calculate that, and we need to do this without a calculator. So we don't have to draw a triangle, but just to help you review, we can do that. So pi over 3, we need to understand what angle that is, so let's look up here. We can see that's 60 degrees, right? And maybe I'll copy this and bring it down for us. You should have a picture of this. I don't think I really have room for that, so that's kind of pointless, I guess. But yeah, that's 60 degrees. So that would be about there. And so this angle is pi over 3, and I'm just going to write in degree units. So this angle must be 30 degrees because of the triangle sum theorem. All the angles have to add up to 90 degrees, right? Excuse me, they have to add up to 180 degrees. The 30, 60, 90 degree triangle theorem is something that we're going to need here. We'll also need the 45, 45, 90. So if you need some help remembering these, you need to take a picture of these theorems. So the 30, 60, 90 degree triangle theorem tells us that if this side is b, then this side is b times root 3, and this side is 2b. Alright? So sine pi over 3 is the same thing as sine 60 degrees, which is just, well, sine is defined to be the side opposite the reference angle divided by the hypotenuse. And I'm going to make the reference angle green. Usually we make the reference angle green in this course. Okay, so now all we have to do is cancel out the b's, so we have root 3 over 2, and that's the answer. Okay, so let's try some more of these. As you can see, this is really not that hard. Now we have pi over 4 here. Remember, pi over 4 is 45 degrees. So if you multiply that by 3, 3 times 45 is 135. So this is the same thing as cosine 135 degrees. And so we're going to move out this way. So the reference angle is going to be 45 degrees. This angle here is that is 135 degrees. And so by the triangle sum theorem, this angle must be 45. This angle is obviously a right angle. And the 45, 45, 90 degree triangle theorem, which we looked at over here, that tells us that if this side is b, then this side must be b also, and this side must be b root 2. But there's something that I forgot. This side has to be negative. So cosine is the side adjacent the green reference angle divided by the hypotenuse, and the b's cancel out. You're left with negative 1 over root 2, and then if we multiply both sides of the fraction by root 2, we can rationalize the denominator. So just a little bit of trigonometry review. Let's try a couple more of these before you try one on your own. Now, you'll notice if you're looking at your radian units, your special angles, pi over 6 is 30 degrees. So 7 times pi over 6 is 7 times 30 degrees. So that would be the equivalent of 210 degrees. So we're going to rotate 210 degrees, which would bring us all the way over here, roughly. Maybe not that much. About there, roughly. And so the reference angle is obviously going to be 30 degrees. And this angle is 60 by the triangle sum theorem. And the 30, 60, 90 degree triangle theorem tells us that if this side is b, then this side is b root 3, and this side is 2b. But I've forgotten to do something very, very crucial, very crucial. This number and this number are going to be negative. Now remember, the hypotenuse is never negative when you're calculating the values of these trigonometric expressions. But this side is negative because it's to the left of the y-axis, and this side is negative because it's below the x-axis. Again, this should all be review for you. So now, what is cotangent? Cotangent is the side adjacent the green reference angle divided by the side opposite the green reference angle. The b's and the negatives cancel out, and you're left with root 3. So what this means is we can calculate these values without a computer. You don't need your TI-84 Plus or your iPhone or your Hewlett-Packard or your Casio or whatever. Okay, so let's try one more of these. Now again, pi over 4 is 45 degrees, so 7 times 45 degrees would be 315. So let's draw that angle. That'd be roughly here. Doesn't have to be perfect. You don't have to use a protractor. So secant 7 pi over 4 is the same thing as secant 315 degrees. And we need to know the reference angle. The reference angle is obviously 45, and this angle is 45 degrees. So we have a 45, 45, 90 degree triangle. We can use the 45, 45, 90 degree theorem. And this side has to be negative, don't forget that. So secant is defined to be the hypotenuse divided by the side adjacent the green reference angle, which is b. The b's cancel out and you're left with root 2. So there you go. So at this point in your education, this trigonometry should be fairly straightforward for you. I'm not saying that this is a simple process. It's not by any means a simple process. But you've done enough problems to where you need to be pretty familiar with this. And now we're getting some practice with radian units. So you're going to be more familiar with radian units now. So get a picture of problems 13 and 14, and I'm going to give you one more chance to get a picture of these theorems. Get a picture of all this stuff together if you want. And I want you to use number 15 and 16 to help you do number 17. So try 17. When you come back, we'll do it together. Alright, we're back. So pi over 4, if you look at your radian units, pi over 4 is the same thing as 45 degrees. So that triangle is going to be in the first quadrant. And the reference angle is the actual angle itself. The first quadrant is the only quadrant where that is true. Unless you have a negative angle measure, then the fourth quadrant would be the only quadrant where that's true. So the 45, 45, 90 degree triangle theorem tells us that these are the relations between the sides. So sine 45 is the side opposite the green reference angle divided by the hypotenuse. The b's cancel out, you're left with 1 over root 2. But remember, we can't leave a fraction with an irrational number in the denominator. So we're going to multiply both sides of that fraction by root 2, and we end up with root 2 over 2. So we calculated the value sine pi over 4. So if you got that right, excellent, very good. Go ahead and try number 18. And again, if you didn't get a picture of these, go ahead and get a picture of those. So try number 18. When you come back, we'll do it together. Okay, we're back. So notice that we have pi over 6. That's 30 degrees. But if you multiply that by 5, that means 30 times 5, that would be 150 degrees. And so we're really looking for cosine 150. 150 would be about there, roughly. And so that's going to be our triangle. And our reference angle is going to be 30 degrees. and by the triangle sum theorem, this angle is going to be 60 degrees. So we have a 30, 60, 90 degree triangle. So if this side is B, then this side is B root 3, and this side is 2B. But I forgot something. What did I forget? This side has to be negative, right? Okay, so cosine is the side adjacent the green reference angle divided by the hypotenuse. And so we have negative root 3 over 2. That's the final answer. So if you got that right, excellent. Okay, so go ahead and try number 19, and when you come back, we'll do it together. Alright, we're back. So pi over 4 is 45 degrees. 5 pi over 4 is 5 times 45 degrees, so that would be 225 degrees. So we're really looking for tangent 225 degrees. So let's draw the angle. There's our angle and our corresponding triangle. The reference angle is 45 degrees. By the triangle sum theorem, this angle must be 45 also, and we have a 45, 45, 90 degree triangle. This side is negative B, this side is negative B, this side is B root 2. So we're ready to go. Tangent 225 is the angle, or excuse me, the side length opposite the green reference angle divided by the side length adjacent the green reference angle. So we have 1. So tangent 225 degrees is 1. So if you got that right, excellent. Go ahead and try number 20. When you come back, we'll do it together. Okay, we're back. So pi over 3 is 60 degrees. 5 times pi over 3 is 5 times 60 degrees, which is 300 degrees. So we're really looking for cosecant 300 degrees. And let's draw the angle. The angle would be something like that. Again, you don't have to use a protractor. It doesn't have to be perfect. And the reference angle is 60 degrees. By the triangle sum theorem, this angle is 30 degrees. And if the angle opposite 30 is B, then the angle opposite 60 is B root 3, and the hypotenuse is 2B. That's what the 30, 60, 90 degree triangle theorem tells us. So cosecant 300 degrees is the hypotenuse divided by the side opposite the green reference angle. And I forgot something. See how easy it is to forget the signs? That should be a negative number, you see. Very easy to forget that. So we have negative 2 over root 3, but we need to rationalize that denominator. Let me move this over a little bit. So the b's cancel out, and we have 2 over root 3. Multiply both sides by root 3, and we get 2 root 3 over 3. Sorry that that's kind of scrunched in there. If you got that right, excellent. Good job. So, those were special angles, 30, 60, 45, and the multiples of those angles. But we haven't done problems that have quadrantal angles. Remember, quadrantal angles are angles that are multiples of 90 degrees. So 0 would be a quadrantal angle. 90 degrees is quadrantal, 180 is quadrantal, and 270 degrees is quadrantal. So here we have sine of a quadrantal angle. What is pi? Well, pi is 180 degrees. So all we're doing is just looking for the value of sine 180 degrees. Now, when you have quadrantal angles, you don't draw triangles because the triangles are actually collapsed. So think about this triangle. What's going to happen to it as this orange angle gets closer and closer to 270 degrees? Well, it's going to get closer and closer to the y-axis until eventually it just collapses. So we can't draw triangles for quadrantal angles. What we have to do is use these curves. And notice that I've replaced the degree units with radian units. So what is sine pi? Well, we just count out pi units, and then we ask what is the y value of the corresponding point. And the y value is 0. So sine pi is 0. So we don't really have to even write 180 degrees if we don't want to. But it's probably good to write 180 so we know what we're doing. So that will be 0 degrees. What about cosine pi over 2? Let's look at the cosine curve, move out pi over 2 units, and then ask what is the y value of that point there. Well, it's 0. So cosine pi over 2 is 0. So you should be fairly familiar with this type of math. We've already done this many times in my curriculum. So now it's time for you to try. I want you to get a picture of these curves. Take a picture with your phone. And I want you to try number 23. When you come back, we'll do it together. Alright, we're back. So this is the same thing as sine 270 degrees. And I forgot to show that on this problem. This is the same thing as cosine 90 degrees, which is 0. And sine 270 degrees is -1. So go ahead and try 24. Remember, moving out, we have -1. Try number 24. When you come back, we'll do it together. I'm going to leave those graphs in the window. Okay, we're back. So moving out pi units, the corresponding y value is -1. That was just a coincidence that the answers ended up being the same for both of these. So we're just reviewing basic trigonometry. So I'm going to give you one more chance here. One more chance. Take a picture of these radian units if you have a phone, or draw a picture or whatever you need to do, because you need this information right in front of you. You can also go online. Obviously you don't want to draw a picture. You can go online and find pictures of all this information. Very easy to find this information. And what else do we need pictures of? We need pictures of these graphs. So get a picture of those. And so now we're going to move on to something that we haven't done yet, and that is graph polar equations using radian units. So we've graphed polar equations with degree units for angle measures, but we haven't done it for radian units for angle measures. So we have a polar equation. How do we know it's polar? Well, because we have theta and r instead of x and y. Theta and r instead of x and y. And we could use degree units to graph this, but in this case we're going to use radian units. So it says to write the coordinates of at least 4 points. And it says use a graphing calculator to draw the other parts of the plot. So you're going to need your graphing calculator. So let's graph our first point. So remember, the quadrantal angles are always the best angles to choose, or not always, but in most cases. So I'm going to choose 0. Now notice I didn't write 0 degrees. Normally I would write a degree symbol here, right? I didn't do that because this is not 0 degrees, it's 0 radians. And then I'm going to plug in 0 radians into the function, and now we have to use our graphs up here, because remember, if it's a quadrantal angle you have to use these graphs. So cosine 0 you can see is 1. So r is equal to 2. So now we have our point. It's 2, 0 radians. So we're going to count out 2 units and then rotate 0 radians, so we have our point right there. So that is the first point. And now let's choose, again, we want to stick with quadrantal angles. Now we have to use radian units. The problem specifically tells us to use radian units for the angles. So I know it's easier to use degree units because we're more familiar with those, but in math you really need to be familiar with radian units. So if you look at your graphs, cosine pi over 2 is 0. So we have 0, and so r is equal to 1. Our point is 1 comma pi over 2. And so we need to move out 1 unit and then rotate pi over 2, and that's going to get us to this point here. So that's 2 points. We just need to graph 2 more points. And then we're going to use the calculator to help us with the rest, because it's not practical to graph every single point with these polar graphs, because there's a lot of points. And even after graphing 10, 12, 15 points, we may not necessarily get an idea of what the graph looks like, so it's just not practical. Okay, so let's choose theta is equal to pi. Let's try pi. So r is equal to 1 plus cosine pi. And let's look at our graphs, because again we're using quadrantal angles. So cosine pi is -1. Again, it's the y value of that graph. So we have 1 minus 1, r is 0. So our point is 0 pi. So that's the third point. So 0 pi would be obviously at the origin there. Okay, so now what should we try? Let's try something other than a quadrantal angle. We could use another quadrantal angle, but let's see, how about negative pi over 3? We want to get some other angles rather than just quadrantal angles. So now cosine negative pi over 3, that's negative 60 degrees. So I'll be down here. That's a 60, 30, 90 degree triangle. This side is negative b root 3. This side is b. This side is 2b. This is all stuff that you need to do in your head. I know that's kind of a tall order, but you've seen this so much that you should be able to visualize this in your head. So cosine is the side adjacent over the side, or over the hypotenuse. So that would actually just be 1/2. So it's not practical to draw the triangle every time you want to make those calculations. So you need to start doing that in your head. Okay, so 1 1/2 and negative pi over 3. So we're going to count 1 1/2 and negative pi over 3, which would get us somewhere down here. Okay, so now, do we know what the graph looks like? Do we have an idea based on these 4 points? Absolutely not. We do not. And even if we graph 10 points or 20 points, are we going to know what the graph looks like? Well, probably not. It's just not practical to do this without the aid of our calculator. So we're going to use the TI-84 Plus. If you have a different calculator, you're going to have to go online to figure out how to use that. So you're going to press the mode button at the upper left and go down and make sure you're in Radian mode, and where it says function in parametric, make sure you're on polar mode where it says pole. Then press the blue second button and then mode button again. That quits out of the screen. Now you're going to press the y equals button at the upper left. The stat plot F1 button is the y equals button. Then you're going to enter 1 plus cosine and then the button right below the mode button. That'll give you a theta variable. Then you're going to press the right parenthesis button, or the end parenthesis button. So you should have 1 plus cosine theta. So now we have to worry about our window, so press the window button. Now notice it says negative 180 degrees and positive 180 degrees. That's too many radians. That's going to take your calculator forever to graph this, because now we're in radian units. We don't want negative 180 radians. That's too many. So we're going to go from negative pi to pi. That's the equivalent of negative 180 degrees to 180 degrees. In radian units, that would be negative pi to positive pi. So luckily we have a pi button. So I want you to press the negative button at the bottom right with the parentheses around it. And then I want you to press the blue second button, and then the upside down V button in the middle right. Middle to upper right. That's the exponent button. So you should have negative pi. When you push enter, it's going to change negative pi to negative 3.141592. Then press the down arrow key and do the same thing. The blue second button and the upside down V button, that should give you positive pi. Now the step says 1 degrees, but that's not degrees, that's radians. 1 degree is an okay interval for your theta values if we're in degree units, but it's not okay at all if you're in radian units, because that would be the equivalent of like 57 degrees. So that would mean that your calculator would graph a point every 57 degrees. That doesn't work at all. So you're going to change the step from 1 to 0.01. That should be a sufficient interval for every point on the graph, so we have a smooth graph that is representative of what we're actually trying to graph. So now, in order to enter the window, you can look here. I'm showing you what the window should be. So you see x minimum is -2. So change that to -2. X maximum should be +3. Y minimum should be -2, and Y max should be roughly 2. So then I want you to press the graph button at the upper right, the table F5 button, the graph button, and give it some time. Be patient. It's going to graph what looks like some sort of a cardioid or a lemicon. We don't really care what the name of it is. But now we have a picture that shows us roughly what this is supposed to look like. So remember, this is not an art class, so we don't really care that much if our graph is perfect. We're just looking for the general shape here. And that looks about right. It's not perfect. You're going to notice that my graph is not really perfect, but that's okay. We have the general shape. So there you go. That's how to graph polar equations using radian units. It's the same thing we did in our classes on polar equations, except we're just using radian units. So we're reviewing polar equations and the graphs of polar equations, but we're also reviewing how to use radian units. So before you try one on your own, let's attempt one more of these problems. So as usual, we're going to try 0 radians for theta, and r is equal to 2 over 1 minus sine 0 radians. And what is sine 0? Well, we can look right up here. Sine 0 is 0. You should be very familiar with using those curves. So sine 0 is 0, which means that r is 2 over 1, which is 2, and so the point that we're looking for in radian units is 2, 0. So we're going to count out 2 and then rotate 0, which means that we have that point right here. Okay? So now let's try pi over 2. Remember, we want to stick with quadrantal angle measures if we can. And so r is equal to 2 over 1 minus whatever sine pi over 2 is. So let's look at sine pi over 2. So sine pi over 2 is 1, and it looks like we can't use pi over 2. Do you see why? We have 2 over 0, but that's okay. We can just try a different value. That's fine. Remember, when you have 0 in the denominator, it's an undefined expression. So let's use pi. So 2 over 1 minus sine pi is the value of r, and if you look at your graph, sine pi is just 0. So we have 2 over 1, which is 2, and so the point we're looking for is 2, pi. So we're going to count 2 units this way and then rotate pi, and we'll get this point here. Pi is 180 degrees. Okay, so let's find 2 more points. Let's try theta is equal to, let's try 3 pi over 2. Again, we're going to try to stick with quadrantal angles. So r is 2 over 1 minus sine. 2 over 1 minus sine 3 pi over 2. So let's look at our graph. The sine graph looks like this, and 3 pi over 2 is here, so negative 1 is the value of sine. So we have 2 over 1 minus negative 1, which is obviously just 1. So the point we're looking for is 1, 3 pi over 2. So 1, 3 pi over 2, we're going to count out 1, rotate 3 pi over 2, and we get to there. So now we just need one more point, and at this juncture it's really going to be better to use an angle that is not quadrantal. So I'm going to use positive pi over 3 would actually not be on the scale. So we're going to choose negative pi. did I say pi over 2? I meant pi over 3. Positive pi over 3 is not. So we're going to choose negative pi over 3. I think this might be on the graph. So let's calculate r. Sine negative pi over 3. Well, think about this in your head. We're rotating negative 60 degrees. And this angle is 30. So we have a 30, 60, 90 degree triangle. This side would be b, this side would be negative b root 3, and this side is 2b. Now, sine is the side opposite the negative 60 degree angle divided by the hypotenuse. So that would be negative root 3 over 2. So r is equal to 2 over 1 plus root 3 over 2. And we can enter this into our calculator. I'm going to go up here because we're kind of out of room. If we multiply both sides of that fraction by 2, we get 4 over 2 plus root 3. So this is kind of a complicated expression. You may want to use maybe negative pi over 6 rather than have to deal with this expression. But in order to calculate this, we can press the green alpha button at the upper left, and then the y equals button at the upper left, and then enter, and then we have a fraction template. We can enter 4, and then press the down arrow key, and 2 plus the blue second button, and then the x squared button at the middle left. And then 3, and then right arrow key, and then enter. And that gives us an estimate of what this expression actually is. So that would be approximately 1.071. So the point that we found is 4 over 2 plus root 3, comma, negative pi over 3. And we can use this value to help us plot the point. So 1.071, we're going to go out 1.07, and then we're going to rotate negative 60 degrees, which would give us something about here, roughly somewhere around here. Now again, as you can see, this doesn't really help us see what the graph is. We're just practicing plotting points. We need the calculator to help us. So press the y equals button at the upper left, and you're going to press the green alpha button at the upper left and the y equals button at the upper left, and you should have a fraction template. And by the way, you want to delete everything else in the calculator. Push the delete button in the upper middle part of the calculator. Then in that template, you're going to enter 2, and then the down arrow key, and then 1 minus sine, and then the button right under the mode button, and then the right parenthesis, and then the right arrow key. So you should have 2 over 1 minus sine theta. Then you're going to press the window button. What is our window? Well, the x max is going to be, well, first let's do the x min. That's going to be negative 3. So change that to negative 3. X max is going to be positive 3, it looks like. So make sure that's positive 3. Y minimum is negative 2. Y max is 2. And now we push the graph button at the upper right. And just have patience as the graph is drawn by your calculator. And this is actually going to be a parabola. So let your calculator keep graphing that, and I'm going to connect the dots here. So that's what it is. It's a parabola. Okay, so I want you to take a picture of this information and go ahead and try number 27. Now, I want to give you some advice for number 27. Notice that inside the function we have 2 theta. Make pi over 4 one of your theta values that you choose, because this is going to be a little different because we have 2 theta. So go ahead and try number 27, and when you come back we'll do it together. Alright, we're back. Again, you can see my graph is not perfect, but that's okay. We don't really care, as long as it looks something like what it's supposed to look like. So if you got that right, excellent. So now let's try number 28. Go ahead and attempt number 28, and when you come back we'll do it together. Alright, we're back, and I almost graphed that decently, but there we go. It's not perfect, but it's good enough. So if you got that right, excellent. Okay, so let's try another problem. We're going to graph this polar equation. I know it doesn't seem like that's a polar equation, but it is, because we have theta as a variable instead of an x or a y. And this shows us how to understand what this graph is going to look like. If theta is always 4 pi over 3, then it doesn't matter how many units you count out. You're always going to rotate the same angle, and pi over 3 is 60 degrees. 4 pi over 3 would be 240, so this is negative 240, so we're going to go all the way over here. And if we count out, let's say we count out negative 4, and we rotate negative 240 degrees, then we'd go all the way out to here. But notice that those points, if you draw a line through them, you get this corresponding line. I'll make it purple. And let's try another one. Let's go out 1 unit to the right with the orange, and let's rotate negative 240, and we get to the same line. So it doesn't matter what r is, you're going to land on that purple line. So this is actually the graph of a line, but it's kind of hard to see that. So what we're going to do is use a conversion. Now if you look at this triangle here in the first quadrant, you can see how we convert. We're going to convert to an equation with rectangular variables. So tangent theta is equal to y over x. Remember, we learned that. Now theta is always the same. It's negative 4 pi over 3. So because theta is always the same, we just plug in our theta value. And now we have to calculate tangent negative 4 pi over 3. That's tangent negative 240 degrees. So we can use this graph to help us with that. So we're going to rotate negative 240 degrees, and then we get a triangle that looks something like this. And this side is going to be, well, the reference angle is 60, and this angle obviously has to be 30. So this side is going to be negative b, this side is b root 3, and this side is 2b. So what is tangent negative 240 degrees? It's the side opposite the green reference angle divided by the side adjacent. And of course the b's cancel out, and we're left with negative root 3 is equal to y over x, And how does that help us? Well, if we multiply both sides by x, we get negative x. Well, I'm going to write the root 3 first. Normally we don't want to do that, but in this case I think it's best. So we multiply both sides by x, and we get this expression here. And how can we interpret this? How do we understand this? You know, how did that help us? Because it may not seem like that really did much for us. Well, remember, if you don't have any variables that are squared or variables that are in denominators of fractions, then, well, long story short, if you can put an equation in this form, you know it's a line. So the slope of the line is negative root 3, and of course we have our x value, and b is actually 0. So how do we illustrate that? Well, we can just write plus 0. So b is 0, and I'm going to change these to black letters there. And of course this is y here. So this is just a line. The slope is negative root 3, and I know that root 3 is kind of a difficult number to work with, so you can enter root 3 in your calculator, and we get 1.73 approximately for the slope, 1.73. So I'm going to go up here and write negative 1.732 times x is equal to y. Now, remember, when we graph a line, we think of the slope as the rise over the run. So we can think of that as negative 1.732 over 1. So we have rise over run. This is all just review, so you should know this stuff pretty well. So here's how we graph this. We first mark the y-intercept. The y-intercept is 0. And so maybe I'll write that 0 also, just so we know the y-intercept is there. So the y-intercept is 0, so we mark that point. And then we move down 1.732 because it's negative. That's the rise, and the run is 1. Then we get our next point, and we can do the same thing going in the other direction. So again, the rise is negative 1.732, which is actually going down, it's not rising, and then the run is 1. So again, you start with your y-intercept, you mark that point, and then you use your rise over run. So now we can just connect the dots, and we're done. I'm going to use a smaller pen there. So believe it or not, that's actually this graph. So that kind of took us a long time to explain, but you don't have to take that long to do the problem. If you understand the basic concept, you can just graph it in about 10 seconds. But I just wanted to review all that information for you. So that was a special angle. This is not a special angle. So we're going to do some things a little differently. So again, tangent theta is equal to y over x. That's our conversion, one of the tools that we use. And you don't have to convert to rectangular units, but you can see it's kind of helpful to see what this graph really is. Theta is always pi over 5, so we just change theta to pi over 5. And now we have to use our calculators to find tangent pi over 5. So you're going to press the tan button, then the blue second button, the upside down V button at the middle right. That'll give you the pi symbol and then divided by 5, and then the right parenthesis button at the middle right. So you should have tangent pi over 5, press enter, and you get 0.7265 approximately is equal to y over x. Multiply both sides by x. And this is approximately what we get. That's just a line. That's all that is. So we can write in a form that is familiar to us. So this is mx plus b is equal to y. That's slope-intercept form. So maybe we should use the same colors: blue, green, purple, yellow. So blue, green, purple, yellow. Obviously you don't have to use these colors. I'm just trying to make this clear what is going on here. So we just have to graph this. So we start with the y-intercept. Whenever you're graphing a line, you start with the y-intercept. The y-intercept is just 0 in this particular case. Then we're going to move up 0.72. That's the rise, and to the right 1. And the same going down. And I forgot to write 0.7265 over 1. This is the run. So the rise is 0.7265 and the run is 1. And so now that's all we really need. We can connect the dots. Try to have a steady hand there. If you have to redraw it a couple times, that's fine. So there you go. So these are just a few examples of some of the equations that you may need to graph. So I want you to try number 31. 31 has it's a special angle. So try number 31. When you come back, we'll do it together. Okay, we're back. Again, this is all just review information here. So if you got that right, excellent. So I want you to get a picture of this information here. And this next problem, you're going to need a calculator because this is not a special it's not a special angle. So again, you're going to use tangent theta is equal to y over x so we can understand what this graph looks like. Try number 32. When you come back, we'll do it together. Okay, we're back. And so now we can connect the dots, and there you have your graph. So if you got that right, excellent. Okay, so now we're going to learn the complex plane, but before we do that, we're going to review imaginary numbers and complex numbers. Imaginary numbers have I as a factor, and complex numbers have I as a factor, but a real component, the green numbers, added to them. So they have an imaginary component and a real component. Remember, the real numbers are the normal numbers that we're used to. So for all intents and purposes, that's how you can think of imaginary numbers and complex numbers. But to be honest, it gets kind of confusing because actually most numbers are considered to be complex. For example, 10 is complex. 6i is complex. Most numbers fall under the umbrella of complex numbers. But for all intents and purposes, if a number has I as a factor, it's imaginary. If it has I as a factor and another number added to it, it's complex. Again, I know that's very confusing. So let's do some review here. We have complex numbers that we're adding. We have a complex number here and a complex number here. We don't really need the parentheses, but we just use those to show that we're adding two complex numbers together. So we're going to add the real component first. 1 plus negative 3 is negative 2. And then we're going to add the complex component. So negative 5i plus 2i is negative 3i. So we added those two complex numbers. Now let's subtract. You have to be really careful when you subtract a sum or a difference. Remember, you have to change the sign of all the terms that you're subtracting in the sum or the difference. So 6 minus 9 is negative 3, and 3i minus I is 2i. So we subtracted. Now we're going to multiply. We're going to use distribution. So we're going to multiply negative 6i by 8 and by 4i. So negative 6i times negative 8 is positive 48i. And negative 6i times 4i is negative 24i squared. Now, one of the most important characteristics of I is that when you square it, you get negative 1. Do you remember that from my intermediate algebra course? We also, I think we went over that a little bit in this course when we studied polynomials. So now we have 48i plus 24, and traditionally the real number is written first, and we'll talk about why that is a little later on in this class. So we'll just switch those numbers. Okay, now we're multiplying two complex numbers, and you can consider those to be binomials, even though they're not really binomials because we have an imaginary component here. So we're going to use FOIL. So 2 times 4 is 8. 2 times negative 7i is negative 14i. 5i times 4 is 20i. And 5i times negative 7i is negative 35i squared. So now we can combine like terms. Negative 14i plus 20i is 6i. And I squared, as we talked about previously, is negative 1. That's what makes it imaginary. So we have 43 plus 6i if we multiply those complex numbers. So let's make sure we did that correctly. Let's double check. Remember, you always have to double check. And it looks correct. So now I'm going to give you a chance to do some of those problems. You can use numbers 33 through 36 to help you. So try number 37, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. So go ahead and try number 38. When you come back, we'll do it together. Alright, we're back. So if you got that right, excellent. Traditionally, we want to write the real number first, and then the imaginary number. It's not wrong if you do it the other way, but it's better to follow the tradition in this case. So try number 39. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, try number 40, and when you come back, we'll do it together. Okay, we're back. We want to write the real component first, so we write negative 26 minus 2i. So if you got that right, excellent. Okay, so that was just a little review on complex numbers. And the reason that we did that is we're going to study something that is actually pretty easy. We're just going to go through this quickly. It's not really that important in the math curriculum. but it's something that you might see, so I just want you to know how to do this. This is really easy. We're going to graph complex numbers. Now, normally when you graph something, you have ordered pairs. For example, you might have 2, 4, and this is the horizontal movement and the vertical movement. So you have numbers separated by a comma, right? Well, when you graph a complex number, you don't have a comma. You don't have two numbers like 2 plus 4i, comma 3 minus 6i. That's not how complex numbers are graphed. When you graph complex numbers, the real number is considered to be the horizontal movement, and the coefficient of the imaginary number is considered to be the vertical movement. So if you're going to graph this, you would move out 2 units to the right, and then 1, 2, 3, 4 units up. So that is the graph of this complex number. Now, probably the main question that you're going to ask is, why? Why are we doing this? Why are we considering these numbers to be the horizontal and vertical movement on some plane? And why do we have a real axis and an imaginary axis? This is just one number. How can we graph points when we only have one number here, as opposed to two numbers separated by a comma? This is just bizarre stuff, and it is bizarre. It's very strange, and the question is, again, why do we do this? Well, again, this is not something that's really that important in the math curriculum, but the reason that mathematicians do this is that there are certain sets, and a set is just a group of numbers. There are certain sets that mathematicians have studied that give us some really interesting graphs when you try to graph complex numbers in this particular way. And that's why this has become such a point of interest among mathematicians. And again, I want to keep reminding you, this is really not that important for the general math curriculum. It's just something that you may see, so we have to learn how to do this. Let's graph a few more points, and then I'll give you some information where you can see why mathematicians have become interested in this way of graphing complex numbers. So here we have -1. We're going to go to the left and then 3 up. So it's just like graphing the way that we learned in pre-algebra. Here we have -2. We're going to go to the left 2, but then we're going to go down 5 because we have a -5. So 1, 2, 3, 4, 5. And here we have +3, so we're going to go 1, 2, 3 units to the right, and then -2, so we're going to go down. And so as you can see, this is really easy. Now, we have, again, a real axis, and we have what we call an imaginary axis, and the combination of these two are what we call the complex plane. Okay? So, before we talk about why this is done, I want you to go ahead and try number 45. I know this is kind of easy, but I just want you to do a few of these problems, and we'll be done with the class. So try number 45, and when you come back, we'll do it together. Okay, we're back, so we're going to move out 1, 2, 3, 4 units to the right, and then 1, 2, 3 up, and that is our point. So you can see that this is really easy. So try number 46. When you come back, we'll do it together. All right, we're back. So we're going to move to the left 1 and then down 1, and that is our point. Very easy. So try number 47. When you come back, we'll do it together. Okay, we're back, so we're going to move 1, 2, 3, 4, 5 units to the right, and 1, 2, 3, 4 units down. So there you go. If you got that right, excellent. Try number 48. When you come back, we'll do it together. Alright, we're back. So we're going to move 2 units to the left, and then 2 units up, and we have our point. So as you can see, graphing complex numbers is really not that difficult. But again, why do we do this? This is very strange. Well, in order for you to find some more information on this, I'm going to recommend a video on YouTube, and it's by a guy named Jason Lyle. You don't have to watch the video if you don't want to, but type in Jason Lyle and the Mandelbrot set. You may recognize that phrase, Mandelbrot set. There was a guy named Mandelbrot who found that when you graph certain groups of complex numbers, you come up with some really interesting graphs. And these graphs were so interesting that this set became very famous among mathematicians. And Jason Lyle is, I believe, an astrophysicist, and he has a digital program and a very good presentation where he shows why the Mandelbrot set was so interesting to mathematicians. So again, you don't have to look at that if you don't want to, but I just wanted you to know how to graph complex numbers in case you come across this in the math curriculum. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and number 4 and number 5, 6, 7, and 8. But don't go before you get your homework. So here's the homework assignment. Remember, the homework is not optional. There's screenshot number 1 and number 2 and number 3 and number 4. But don't go before you get the answers. It's not enough just to attempt the homework. It must be done completely and correctly. So if you get a wrong answer, go back and figure out what you did wrong, or else the homework is a complete waste of time. So here's screenshot number 1 of the answers to the homework. And here's screenshot number 2. So get that homework done completely, correctly, neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.